Welcome to the deep dive. Today, we're going deep on analog computing. We'll be exploring what it is, why it matters, and what the future might hold. You've given us some really great source material this time, including a paper by Levny Moten, who makes a pretty bold case for analog computing.
Interesting stuff.
Yeah, and we also have his resume, so we can get a sense of where he's coming from. So could analog computing really disrupt the digital world? What are the strengths and weaknesses of each approach?
Good questions.
Can we learn anything from the human brain, which is itself a crazy efficient analog system? Let's find out. Joining me today is an expert on this topic.
Happy to be here.
What do you think is the most important thing to understand about analog computing right off the bat?
I think it's that analog computing isn't something new. Like, it's not some futuristic concept. It actually predates digital computing. It's based on a totally different way of processing information.
Okay, so let's unpack that for a second. We're so used to the digital world of ones and zeros. How is analog different?
Well, think about like a dimmer switch controlling how bright a light is.
Okay, yeah.
That's analog. It's a continuous signal that can change smoothly. But digital, that's like a regular light switch. It's either on or off, right? No in between.
So instead of bits, analog computing uses signals like voltage or pressure to represent data.
Exactly. A great example is an old school mercury thermometer. You know the kind.
Yeah, I can picture it.
The height of the mercury changes continuously with the temperature. That gives you a direct analog representation. Before digital took over, we used analog devices for everything.
I can just imagine my grandpa using a slide rule,
Oh,
meticulously lining up those markings to do calculations. That was analog computing, right?
absolutely. Slide rules used physical lengths to represent numbers and do operations.
Mhm.
It shows how analog computing represents data in a physical, continuous way.
All right, I'm starting to get the hang of this. Now, Dr. Moten's paper really stood out to me. He claims that analog computing could be the key to solving some of the biggest problems facing digital computing, especially when it comes to AI. Let's dive into that. He talks a lot about energy efficiency. Why might analog have an edge there?
Well, the energy demands of AI, especially training these huge neural networks, it's crazy how much they use. It's becoming a real problem. Analog computing can be super energy efficient, especially for the complex calculations involved in AI.
So, in a world that's increasingly worried about energy consumption, this sounds like a huge deal, right? Could this be the key to more sustainable AI?
Definitely. Think about the energy it takes to train a huge language model like ChatGPT. Dr. Nemoten suggests analog could do that using way less power. We're not talking about just a little bit better. This could be a total game changer for AI sustainability.
Wow, that puts it into perspective. But energy efficiency isn't the only advantage Dr. Nemoten highlights. He also talks about how analog systems are really good at parallelism, which is crucial for AI tasks like image recognition. Can you walk us through that a bit?
Sure. So digital computers process information sequentially, right? One step at a time, but analog can process information in parallel, doing lots of things at the same time. This makes them perfect for tasks like image recognition, where you need to analyze many different parts of an image all at once.
So it's kind of like the difference between reading a book word by word versus taking in the entire picture at once.
Exactly. For AI that needs massive parallel processing, analog computing could be so much faster and more efficient.
Now, before we get too excited about analog computing, I think we should take a step back and see who's making these arguments. We have Dr. Nemoten's resume here, and it's pretty impressive. What can you tell us about his background? Is he legit?
Oh, yeah. He's not just some random tech guy. He has a PhD in mechanical engineering, and he's had a long career in research and practical engineering. He's worked at places like Brookhaven National Laboratory and held leadership positions in computing and mathematics for decades.
So we can be pretty confident that he knows what he's talking about. His background definitely gives him credibility when it comes to analog computing. All right, so back to the potential of analog computing. One thing that intrigued me in the paper is how well analog computing seems to work for certain types of algorithms, particularly those used in solving differential equations and simulations. What makes analog so special in these areas?
It's all about how analog systems represent data. They use continuous signals, so they naturally speak the language of differential equations, which describe how things change continuously over time. They're like designed to model the dynamics of the natural world.
So for tasks like modeling complex systems like the weather or simulating how physical objects behave, analog could be a more natural fit than digital.
Absolutely. Let's say you're trying to model something complex, like weather patterns.
Hmm.
It involves a lot of differential equations, and analog computing really shines there.
Like it's speaking the same language, yeah.
Yeah. Digital computers have to approximate these continuous processes, which can be computationally expensive and less accurate.
I see. So analog has a real edge when it comes to these kinds of problems. And there's another point in Dr. Nemoten's paper that blew my mind. The idea of combining analog and quantum computing. It sounds kind of like science fiction.
It does, doesn't it?
Yeah.
But it's an area with so much potential.
Yeah.
Both analog and quantum computing work in a continuous way, unlike digital. Combining them could lead to amazing new systems, things like cryptography or really complex modeling.
So we're talking about harnessing the power of both the continuous nature of analog signals and the craziness of quantum mechanics.
Exactly. It's early days, but the possibilities are fascinating.
Okay, so far, analog computing sounds pretty amazing. But there have to be some downsides, right? No technology is perfect. What are some of the things that might prevent analog from being widely adopted?
Well, one of the biggest challenges is precision. Analog signals, they're kind of sensitive. They're more susceptible to noise and errors than those clean, precise digital bits. It's kind of like the difference between a super clear digital photo and a blurry old analog photo.
Oh, okay.
For applications where you need really high precision, this can be a big problem to overcome.
So analog is great for some tasks, but it can't just replace everything digital, right?
Right. And there are other challenges, too. Like, we're so used to how easy it is to mass-produce digital chips. But building large-scale analog computers is much more complex and expensive.
I bet scaling up analog manufacturing would require a lot of changes to infrastructure and the way things are made, right?
Absolutely. And then there's the whole thing about programming. It's totally different. Programming analog computers requires a different mindset and different skills than programming in the digital world. It's like learning a whole new language.
So if we somehow switch to an analog world, all the programmers would need to go back to school.
Pretty much.
Yeah.
It would be a huge shift.
And of course, there's the giant digital world we already have, our software, networks, everything. Moving to analog would be huge, wouldn't it?
It's like trying to reroute all the rivers and highways on a continent.
Yeah.
It's not impossible, but it would be incredibly difficult.
Yeah.
We're talking about changing everything from how we store data to how we design software.
Okay, so there are definitely some serious obstacles to overcome. But Dr. Nemoten doesn't seem discouraged. He offers some potential solutions in his paper. Do you think they're feasible? Could we actually overcome these challenges and move into an era of analog computing? Let's talk about those next.
Yeah, he definitely sees the challenges, but he also gives us a pretty good roadmap for how to get past them. It's a multi-pronged approach, really, focusing on things like material science breakthroughs, AI-driven design, interdisciplinary inspiration, and targeted applications.
Okay, that sounds pretty comprehensive. Can we break that down? Let's start with material science breakthroughs. What's he proposing there?
Well, he's basically saying we need to put more effort into developing new materials that minimize the noise and instability that analog signals have. We need to make those signals less fuzzy, like we talked about.
Right.
This could mean using things like neuromorphic chips,
Yeah.
which are basically electronic components that work like neurons in the brain. Or memristors. Those are like resistors that have memory.
So instead of trying to make analog signals act like digital bits, we need materials that can work with those analog characteristics.
Exactly. We need to really embrace the unique qualities of analog signals and find materials that can unlock their potential,
I like that. It's like instead of fighting nature, we need to learn from it and change our technology to match. Okay, what about AI-driven design? How could we use AI to help build better analog computers?
Well, imagine using AI to help design and configure analog circuits, like optimizing them.
Oh, okay.
AI could analyze tons of data and find patterns that we might miss. It could lead to more efficient and robust designs.
So it's like AI designing AI, which we talked about before.
It is, yeah. It's kind of recursive, but it makes sense, right?
Yeah, definitely.
It's using the best tools we have to push the boundaries of what's possible. We already use AI to design digital chips, so it's really a natural next step to apply it to analog circuits.
Okay, that makes sense. What about interdisciplinary inspiration? Where should we be looking for ideas?
He thinks it's really important to look beyond just computer science.
Yeah.
We should look at biology, neuroscience, even quantum mechanics.
Oh, wow. Yeah.
For example, we can learn a lot by studying how the human brain processes information. The brain is an amazing analog system. It can do incredibly complex tasks, and it uses so little energy.
Yeah.
That could lead to totally new architectures for analog computers.
It makes a lot of sense. Nature's had billions of years to figure this stuff out. What about quantum mechanics? How could that help us design better analog computers?
So quantum mechanics is all about how stuff behaves at a really, really small scale, right? Like the atomic level. And down there, things aren't as clear-cut. Particles can exist in multiple states at once.
Oh.
It's called superposition. A quantum bit, a qubit, can be both 0 and 1 at the same time. That's kind of similar to the way analog signals work. They're a continuous nature.
So we could maybe find totally new ways to process information by looking at quantum mechanics and analog computing together.
Exactly. It's all about pushing the limits of what we think is possible.
Yeah.
And looking for ideas in new places.
I like that. Okay, last one. Targeted applications. What should we focus on in terms of like real-world uses for analog computing?
Well, he suggests focusing on areas where analog has a clear advantage, like AI, especially for things like training neural networks.
Right.
Like we said before, analog can be super energy efficient. That could be a huge deal for AI.
For sure. Anything else?
Yeah, real-time processing is another area where analog could be great. Think about things that need to happen instantly, like controlling robots or analyzing data from sensors. Analog can process information constantly. You don't need to wait for a clock cycle like in digital. That makes it great for real-time applications.
So analog could help us build robots that can react really fast and adapt to their surroundings.
Totally. And Dr. Nemotin also mentions things like optimization problems.
Okay.
These are problems where you need to find the best solution out of a bunch of options. Analog can explore all those possibilities simultaneously, so it can be way faster than digital.
Wow, there's a lot of different applications. Analog could make a difference in so many fields.
It could be huge, yeah. But, like we've talked about, there are challenges. And Dr. Nemotin is really upfront about that. A big part of his paper actually outlines all those hurdles. He doesn't just paint a rosy picture. He grapples with how hard it will be to make analog computing work in the real world.
I like that about him. He's being realistic.
He is. And I think that's one of the best things about his paper. He doesn't shy away from the tough questions. But he still gives us a path forward, you know.
Totally. Okay, so let's really dig into these challenges. We've touched on them a bit, but I think it's worth spending some time understanding how big they really are. What do you think is the biggest thing holding analog back from becoming more widely used?
It's tough to pick just one. But I think it's the fact that everything is already digital. Like our whole digital infrastructure is a huge hurdle. Everything we have, our software, our data storage, our networks, it all runs on zeros and ones.
Yeah, that's true.
Moving to a world where analog is the main thing would be a massive change. Not just in technology, but in how we think and how we live.
It's like our whole world is built on digital computing, and we'd have to start over almost.
Yeah, kind of. It's a huge challenge, but it's also a really cool opportunity to reimagine what's possible, you know?
Yeah, I get that. Okay, let's move on to another challenge, one we talked about earlier, programming. You said that programming analog computers is really different from programming digital ones. Can you talk more about that? What are the main differences?
Well, in digital programming, it's all about those bits, right?
Mhm.
It's giving the computer super precise instructions. It's all very logical and structured. But analog programming is more about understanding continuous signals and how to control them.
Oh,
It's a different way of thinking. It's like you're working with the real world where things aren't perfectly precise. Feedback loops are really important too.
So it's less like writing code and more like tuning a musical instrument, like finding the sweet spot.
That's a great way to think about it. You have to really get how the physics work
Yeah.
and be willing to experiment to get it right.
Do you think there are many programmers out there who can do that kind of work?
Not many. It's a very specific skill. Right now, most programmers know digital systems. If analog is going to take off, we're going to need a lot more people who can build and program these new types of systems.
That's a good point. We can't just focus on the technology itself. We need to think about the people who are going to use it.
Exactly. We need to make sure people have the skills to succeed in a world where analog is a big deal.
Now let's get back to that issue of precision. You mentioned that analog signals are more susceptible to noise and errors than digital ones. What does that mean for real-world applications?
For some applications, like really precise scientific calculations or financial stuff, accuracy is everything, right? Even a small error can mess things up. Digital's way better for that. Digital signals are much less noisy,
Yeah.
and you can easily fix errors with error correction codes.
Right.
So analog might be awesome when you don't need a perfect answer, like with image recognition or real-time control.
Okay.
But when you need things to be super accurate, it's probably not the best choice.
So it's really about choosing the right tool for the job.
It's exactly.
Last thing on challenges, building analog computers. We talked about how easy it is to mass produce digital chips. Why is it so much harder to do that with analog circuits?
Well, analog circuits are just really picky. Like, they're very sensitive to any little change in the components. Any imperfections in the manufacturing process can affect how well an analog circuit works. Digital circuits are much more forgiving. It's either on or off, so small changes don't really matter.
So it's like the difference between building something out of Legos versus a bunch of random rocks. With the Legos, it all snaps together perfectly. But with the rocks, you gotta really work to make them fit together and be stable.
That's a great analogy. If we want to build big, complex analog computers, we need a level of precision and craftsmanship that's really hard to do on a large scale.
So if we want analog to become mainstream, we need to find ways to make manufacturing more reliable and something we can scale up.
Exactly. We need new techniques and materials that can handle how complex analog circuits are and still be made in large quantities.
Okay, so the challenges are definitely there and there's lots to do. But we are talking about something with huge potential. Dr. Nemotin paints a really exciting picture of a future with analog computing.
He does, yeah.
AI as good as the human brain. Robots that can learn instantly. Huge simulations that could create entire virtual worlds. It's pretty mind-blowing.
It definitely makes you think, yeah. But before we get too lost in the sci-fi stuff, maybe we should look at the things that could happen sooner. What are some ways that analog computing could change our lives
Yeah.
in the, near future?
Well, I think one place we might see analog computing make a difference pretty soon is in those little devices,
Okay.
like smartphones and sensors, the things that process data right there on the device without needing the cloud.
That's called edge computing, right?
Exactly. And analog could be a big deal for edge computing. All that energy efficiency could really change things. Longer battery life,
Yeah.
and it could make new things possible, things we couldn't do with those power-hungry digital chips. So our devices could do more of the work themselves instead of sending everything to the cloud.
Exactly. Imagine a smartwatch that can do, real-time health monitoring using fancy AI algorithms. And it doesn't need to be charged every 5 minutes.
Right.
Or think about self-driving cars, making decisions in a split second based on tons of sensor data, all without needing the cloud.
Yeah, that makes sense. And these kinds of things could really change all sorts of industries, right?
Oh, absolutely. Think about healthcare.
Okay.
Analog computing could lead to these tiny, low-power medical devices that can do all sorts of things, like complex diagnostics, even personalized treatments. Maybe we could move away from these big, centralized healthcare systems and have more care that's focused on the individual patient.
That would be huge. What about other places where analog might make a difference soon?
Well, scientific research is another big one. Like we said before, analog computers are great at simulating complex systems.
Right.
That can mean big breakthroughs in things like discovering new drugs, creating new materials, even modeling the climate.
Can you give me an example? How would that actually work?
Sure. Imagine using an analog computer to simulate what happens when you introduce a new drug to a human cell.
Okay.
That could help researchers find promising new drugs much faster than the way we do it now. Or you could use analog computers to model how complex materials behave. That could help us make lighter, stronger, more sustainable materials. Stuff for airplanes, buildings, all sorts of things.
Wow. So analog computing could really help us tackle some of the biggest problems we're facing.
Yeah, it has that potential.
Yeah.
But, and I know we've said this a lot today, it's important to keep things in perspective.
Right.
It's not a magic solution. We need to remember both the good things and the limitations of analog computing.
Totally agree. It's not going to solve every problem, but it's a tool. And if we use it right, it could lead to some really amazing advances in tons of fields. Speaking of advances, we can't end this without at least mentioning those wild sci-fi ideas Dr. Nemotin talks about. AI as efficient as our brains, robots that learn instantly, those massive simulations that could create whole virtual worlds.
I know, right?
It might seem crazy, but it's so interesting to think about.
It is super cool. And while we do need to stay grounded and remember the challenges, I think it's also really important to be open to these big, crazy ideas like, What if they're possible? We should explore that.
So let's speculate a little.
Yeah.
What would it be like if these sci-fi things actually happened? How would it change things for us?
Imagine a world where AI can learn and adapt as fast as we can.
Whoa.
And they're not limited by digital computers anymore. They might even become better than us at things like solving problems, being creative, even understanding emotions. It makes you think about what it means to be intelligent, to be conscious, to be human.
It's kind of scary to think about, isn't it? What if we create machines that are smarter than us?
It is a little bit, yeah.
Yeah.
But it's also a challenge we need to face head on. We need to be responsible if we're going to develop these powerful technologies. We have to understand the ethical side of things.
That's really important. Technology is just a tool, and like any tool, it can be used for good or bad. It's up to us to make sure analog computing is used to make a better world for everyone.
I totally agree. We're all responsible for that.
Well, I think we've covered a lot in this deep dive. We talked about the basics of analog computing, the good and the bad, the things it could be used for, and even what it could mean for the future. It's a lot to take in, but hopefully you're leaving with a better understanding of analog computing.
I hope so. It's been great conversation. And as you learn more about analog computing, I encourage you to keep asking questions. Don't be afraid to challenge what you think you know and stay involved in the conversation about the future of computing. After all, we create the future.
That's a great way to put it. And on that note, we've reached the end of our deep dive into analog computing. Thank you so much for joining us, and keep those minds curious and those imaginations going.